So what we're looking at here is collisions in 2 dimensions. Just tell me 3 minutes. Collisions in 2 dimensions. So what we're going to do is we're going to start with the cue ball on a pool table, the white ball. And the white ball actually has a mass of about 0.26 kilograms. That's the official mass of a cue ball. And the cue ball is going to be shooting towards another ball. Let's make it the 8 ball. So there's the 8 ball. And the 8 ball has a different mass. The cue ball is heavier than all the other balls. I don't know if you know that pool table. It's 0.15 kilograms. The other thing I'm going to tell you is that the speed of the cue ball originally is 3 meters per second. So after they collide, here's a little dotted line. This is where the collision happens. After the collision, the 8 ball is going to shoot off at an angle like this. So this represents where the 8 ball is after the collision. And it will have a new speed of 2 meters per second. And to help us see exactly what direction that is, we're going to put an angle of 30 degrees here. The white ball, after the collision, is going to shoot off in this direction. So this would be the cue balls after the collision. So before the collision, the 2 balls are stationary. Afterwards, both balls are moving at angles. And we're going to try to determine what the momentum or the velocity is for that final cue ball. So let's say V. We're looking for the velocity of this cue ball after, which means we have to include both its magnitude and its direction. So that's the problem that we're trying to solve. Okay? So, just like any question with momentum, we start off with the simple statement that the total momentum before must equal the total momentum after. And the momentum before is the sum of the momentum of the cue ball times the velocity of the cue ball plus the momentum, I meant mass, right? The mass of the cue ball times the velocity of the cue ball, the mass of the 8 ball times the velocity of the 8 ball. That's what's happening before. Afterwards, these 2 objects will also have momentum, the cue ball, and it will have a different velocity, which we indicate by putting the little prime sign. And then we have the mass of the 8 ball, and it will have a different velocity, which we'll put here with a little prime sign. Nothing looks any different from the linear question to this 2-dimensional question. We can even put in the numbers. So the cue ball would be 0.26, and its initial velocity is 3 meters per second. And I'm going to give it a direction. I'm going to assign standard directions so that this direction for the cue ball will be 0 degrees to the right. So I'll put the direction of the cue ball as 0 degrees in there, because the directions are very important. And then the 8 ball has a mass of 0.15, but initially it's staying still, so it has a velocity of 0. Afterwards, the cue ball's mass does not change, but there will be a new velocity associated with it that I'm not sure about. That's what I put in red, right? Up here, velocity of the cue ball. And then afterwards, I can describe the 8 ball as 0.15 times its new velocity, which was, if we go back, 2 meters per second, at an angle of 30 degrees, which is in standard position already. So 2 meters per second at an angle of 30 degrees. So the only thing that looks different is these angles, right? So let's continue this. 3 times 0.26, 3 sixes are 18, 3 times 2 is 6, and 1 is 7. So 0.78 is what this would be, and it would still be 0 degrees. Now it's a momentum, because I've multiplied the velocity, or at least the magnitude of the velocity, times the mass. And then over here, this is a 0, and then over here, if I have 0.26 times the velocity of the cue ball after, and then here, 0.3 at 30 degrees. Now, if we were doing this with just a linear system, we would just move the 0.3 to the other side and subtract it from 0.78 and get 0.58. But you can't do that in 2 dimensions because those directions make everything a little bit different. We have to think about triangle math, trigonometry. So we're going to move that to the other side, just like we would in a regular equation. And this is what we would end up with. And now, in order to do the subtraction on the left side here, over here, we have to think about doing a vector triangle. And since it's a subtraction, we're going to do a tail-to-tail vector triangle. So, the first term, or one of them, is 0.78 at 0. So why don't I put that right here, and call that 0.78, and I'll just put a reference marker here to show that it's going 0 degrees. Then I'll put the other one tail to tail, but it's only 0.3, so I'm going to put it, maybe about half that. So there's 0.3, tail to tail, and because it's at a 30-degree angle, I know that I have 30 degrees inside here. So that's sort of my vector subtraction, which helps me figure out the left side of this equation. Well, the answer to a vector subtraction is the line between the two vectors like this, and it always points in the same direction as whoever came first in the expression up above. So that means it has to point this way. Now, if you look at that red line, and you look at the red line we drew just arbitrarily in our picture, it kind of looks like it's going the same way, doesn't it? So it gives us a picture. We can look at this and say, yeah, that makes sense. That red line is probably going to give me a good answer. So now we set about solving for the red line. And we do that first by doing cosine law. And so c squared is 0.3 squared plus 0.78 squared minus 2 times 0.3 times 0.78 times the cosine of the angle 30 degrees. I'm squeezing it in there. And if we crunch this number out, we can work kind of backwards and do the cosine of 30 and multiply it by 0.78, then multiply by 0.3 times 2, change it to a negative sign, and then add 0.78 squared and 0.3 squared equals all that, and do a square root. I got 0.54-ish. So C is equal to about 0.54. So I'll put that up here. But I'm not quite finished because I need to also know the direction, right? And so to do the direction, it's a little trickier. This is where we have one of the problems of trig, the ambiguous case of the sine law show up. I'm going to try to use a smaller line here. So we're looking for the angle in here. That's the angle we want to find, because that's the angle I'll use for the red line, the red result. So to do that, we will do, let's do our sine law. We would write 0.78 divided by the sine of that angle theta, which I'll put here, theta. And then that would equal 0.3, oh, sorry, wrong one, 0.54, that's the angle, that's the side that we know with the corresponding angle. and the sine of 30. Now, when we solve for this, this is where we get that ambiguous case. Clearly from our picture, our sketch is pretty accurate. The numbers are in good proportion, and it's pretty clear that our angle theta is bigger than 90. And so the sine law, when you have an angle that's bigger than 90, there are two possible answers, and it always gives you the small one, the one less than 90. So when we crunch this out, let's go 30 sine times 0.78, and divide and do an inverse sine. We get an angle of theta equals 46-ish degrees. And clearly this angle is not 46 degrees, and so we can look at this and we can say it's probably what we call the ambiguous case for sine law, and in order to get the correct angle we would do 180 minus 46, which is 134 degrees. So that's the correct angle that actually matches what we want, right? So now we know that. Now that's the angle theta, but that's not the angle for the red line. We have to measure that on our reference line. So to do that, we've got to kind of imagine what our reference lines would look like here. And we have to sort of zip ourselves all the way around the triangle. Now, if we notice over here, I'll do it in green, if this angle is 30 degrees, this angle is also 30 degrees, right? Do we need that? Maybe we don't even need that.
Yeah, we could.
We could. There's a couple of ways you can do it, right? Well, I guess what we have to do is figure out that this is 60, which leaves us with how much over here? It looks like 74. So we've used our various angle transverse parallel line theorems and whatever we could come up with, complementary angles and so on, to figure out that this piece in the fourth quadrant is 74. And now I can go and measure in standard position all the way around to my red line. It will be 270 plus 74, won't it? It's 270 all the way around to here, and then plus an additional 74. So 270 plus 74 tells me the angle, so 344 is the angle that I want for my red vector. So the answer to this vector subtraction is 0.54, and the standard angle or standard position is 344 degrees. That's about as tricky as it can get when you're playing around trying to find these angles. And of course we had the ambiguous case of sine law, which throws in another wrench. But nonetheless, you have to practice how to handle all these different triangle situations. Now that's not the end of the question. If we go back, this is where students often stop and say, there, I'm done. But all we did is we figured out the subtraction of these two things. We still have all this on the other side of the equation to deal with. So our answer simply represents that subtraction. So now we have to go back and we have to write the rest of the story. So we have figured out that 0.54 at 344 degrees equals what was on the other side, which is 0.26 VC prime, c of the cue ball after. So 0.26 VC prime. Now to do this, you're going to divide 0.54 by 0.26. And that gives you an answer of about 2.1. And when you do that division, you'll end up with meters per second as your unit. Because you're dividing by this number here, which is really just a mass, right? And it's a scalar, does not change the direction at all. So the direction is just carried down and remains the same. And now we've solved the problem and figured out the speed of the cue ball after, well, not just the speed, but the velocity of the cue ball after the collision. So it starts off the same way, but as soon as you get into the adding and subtracting, you have to use the vector triangles. And remember, if you're subtracting tail to tail, than if you're adding tips to tail.